So in 20-1 we started, if you recall. In chapter 19 we got into like electric forces between charged particles. But then in 20-1 we started to look at electric fields more. These next two periods. Yeah, that's what I was saying earlier. If you swing by maybe toward the end of the period, I can call you then if you're between classes. I'll have like 5-10 minutes. That would be around 12:55. So okay, I'll call you back for that. So 20-1 was electric fields, and electric fields, remember, were due to some sort of what we called a source. We use the phrase source a lot. And this was the lab that you guys did with the electric field hockey maze, right? The PhET lab that you looked at. So this formula was E equals K Q over R squared. But the key was to remember that this Q was a source charge. God bless you. And really all we mean by source is a abundance or a larger charge than the neighboring charged particles. So what we'll notice with these problems is that you can have multiple charges in the same area, but one of them that is the strongest is going to be the thing that produces the main field around it. Like the Earth produces gravity around it, and yet you produce gravity around yourself. Your own gravitational field is not significant compared to the Earth's. The same concept applies here. So we've got one larger charge that's giving off an electric field around it. Yeah?
So how is the electric field and then F
Correct. And that was chapter 19. So that's not going to appear on this test in that sense, but let me show you how it will. So if you remember, we also wrote down, I'm going to leave space here to draw a diagram. We also wrote down this formula, which was Fe equals E times Q0. And in this case, if you remember, this was not the source. This was a random, I'll put random charge near the source. Near the source. Not the source itself, but some other charged particle brought near the source of electric charge. So think of again the Earth as the source of electric charge. Think of you being brought near or close to the Earth. If you're near the Earth, you get pulled toward the Earth's surface. Well, the same thing occurs here. If a random charge is brought near the source, it can be pulled toward the source, or, what else? Repelled away from the source. Pulled toward or repelled away.
So if we had a problem where, like you gave us the first round formula as part A, and we had to find E and then use it for the second formula, the Q's wouldn't be the same.
Correct. That's a great question. Here what he asked, if part A was find E, and then part B was find the force between the source and some other random charge, this number is absolutely different than this number, 100%. And this number is going to be like a proton. So it's going to be like 1.6 times 10 to the negative 19 coulombs. Whereas this will be like, I don't know, something on the order of microcoulombs. So like 5 times 10 to the negative 6, a very large charge compared to 1.6 times 10 to the negative 19. Yeah. Okay? And that's how you'll know the difference there. Now let's draw what this looks like. So a positive source, let me put a line here because I'm going to show just diagrams. Okay, those are the two formulas we'll be using. But the positive source, if you remember, how are the field lines drawn for a positive source? How are they physically drawn? Away. Alex, I saw your hand also. Why are they drawn away?
I don't know.
You just know they're going away? Sorry. Why are they drawn away? Why?
They're repelling electrons.
Repel protons. Yeah. Positive source. So remember, the way we think about a field is what would happen if a proton were brought nearby. Well, which way would a proton move if it's brought near a positive source? It would be repelled away. So the arrows are all drawn away from that positive source. Now we could also have a negative source. And the opposite is true for a negative source, right? We know that it's going to be drawn toward because a proton would be pulled toward the negative source. So we have a general understanding or idea about our field diagrams from those two from those two sources given in the figure here. Now, what we also need to recognize is that we could also have a field that is a result of two sources. And we did that as an example in the notes, if you remember. I asked the question, what would the electric field be equidistant from both sources? And I was at the midpoint there. That was one example. I could pick here, I could pick here, I could pick any point, anywhere in between, right? So let's say I were interested in this location right here. Okay, X marks the spot right there. Now, to figure out the electric field at this spot, you need to think about, remember that phrase I used called superposition. Superposition is the idea that if multiple fields act at the same time, we can add them together. It's like multiple forces. If both Bridge and I were to push on this desk in this direction, we both push or hold on it, we would sum together those two forces because we're helping each other. But if Bridge were to push and I push this way, mine would be like a negative force, his would be a positive force. Same concept with fields. So the positive source creates a field at this location that's directed which way? Which way does the positive force direct its field at this spot? Away. So to the right or left in this case? To the right. And we know that because all field lines are drawn away. So even though we're really far away, the field from the positive source is still pushing away. So the field at this location from the positive source is to the right. Well, the field at this location from the negative source is also to the right, because it's pulling the proton that way. So if I were to figure out the overall field at that location, it would be E1 plus E2. I would find the E1 as the electric field from the first source, find E2 as the electric field from the second source. I would need to know R, right? R is the distance. I would need to know Q. Q is the charge of the source. But I would know those values, they'd be given somehow. And I could find the overall electric field at that location, at that spot. Okay? I could have two positive sources, right? I could also look at it this way. And we did this example, and we talked about what happens. I think Chris and Danny, you guys did this in the lab, actually. We could have two positive sources, and if I put a proton right in the middle, what's going to happen to it? What's going to happen to a proton placed right in the middle? It's going to stay stationary. State of equilibrium. Now, we're assuming there's no gravity here, right? Because gravity pulls down. So really, if I were to account for gravity, I would have to put another positive source here to push back up to counter gravity, because gravity pulls down. Or I could put a negative source up top to pull this object up to counter gravity.
Or could you just do a positive and top and bottom?
But remember, if gravity were there, that would be an extra force we have to counter. I'm saying if gravity, but the assumption right now is that there is no gravitational force on this object at all. And as a result, it's going to want to move left, it's going to want to move right, it's not going to move at all. And actually, when we saw yours, it actually was moving, right? But it was kind of like hovering, and it had a vibrating frequency. It was oscillating in space, sitting there, humming, right? Literally sitting there. And that's basically what would happen between this scenario. Now, what if instead, you guys did this, what if instead I took this proton and just moved it a little bit to the right? Just a little. Just a tiny bit. Just a tiny bit. Which field is going to be stronger? The one on the right or the one on the left at this location? Which field is stronger? Why?
Because it's closer.
The closer you are to the source, the stronger the field is, just like the Earth. If I'm further from the Earth, gravity is less. That's Denver, right? Mile High Stadium we've talked about. Or the Rocky Stadium, Coors Field. So those stadiums, they're higher elevation, they're further from the center of the Earth, gravity is less there. Same concept. So yes, as Em said, if I put a proton right here, this is going to be stronger, so it's going to repel. But then it's going to get here, it's going to slow down, and it's going to get repelled. So the minute I put a proton here, it'll just do this. Keep going back and forth. So the starting point of the proton is really indicative of the amplitude of the vibration or oscillation. Think about this object starting here, it's going to be like this. Back and forth. Starting here, it's going to do this. But starting here, it doesn't move. So you guys, when you were doing it with that demo, you can't get it exact, so it's just a little bit to the right, so it started doing that. Okay, but the idea is that one of them would be stronger than the other. But if I wanted you to figure out the field strength, let's say at this location, right, at this location, And let me call the sources 1 and 2, so we have numbers. Well, in this case, E2 would push left. Everybody see that? Think about it logically, and it's really forces you're thinking about now, right? Even though I'm talking about electric fields, this is very much like chapter 19 with forces. If there's an object here that's a proton, it's going to get pushed left from particle or charge source 2. But from source charge 1, it's going to get pushed to the right. So if I were to physically write the values here, it would be E1 pushing to the right minus E2 pushing to the left. Look at the difference between this scenario and the equation we use versus this one up here and the equation or expression that we use there. Okay, in the first scenario, because both fields at this location were pulling or pushing to the right, we sum them. But in this location, one's pushing right, one's pushing left, so there's a difference there, a difference. So if I want to find the overall electric field at any point, I have to use this idea of superposition. Okay, of superposition. Now, again, Sydney asked the question before, but I'll reiterate it. How do we utilize this formula right here? We think about bringing a proton near some sort of a source. It doesn't matter what the source is. So again, if I think about this X over here, think about it as a proton. Okay, let's think about that as a proton right there. So you place a proton in that location, and I want to know what the overall force felt is. Well, to calculate their overall force on a proton, we need the overall electric field, which in that case is E1 minus E2. That was the answer we got. Times the charge on a proton, which is called E. Again, Fe stands for electric force. This E stands for the fundamental proton charge. 1.6 times 10 to the negative 19. E1 minus E2 is the overall field felt at this location, which we wrote up a minute ago. So the overall field times the charge on the particle that's brought to that location will give you the force felt on that particle. Alex?
Can you substitute the E on the top instead of the Fe?
Absolutely, and that's what you would be doing. So keep in mind, Alex, that you would be using this formula right here. Take a look, please. You'd be using the formula you referenced twice. You would first calculate E1 as a result of this source right here. Then you would calculate E2 as a result of this source over here. The difference between these two things is the overall E value, which is why I'm writing it like this. You see what I'm saying? So you would have done this formula twice already to get E1 and E2. Then when you sum them or subtract them, you get the overall E value. That's what this thing is right here. That's the overall E value at that spot. Okay? Emma?
Why does it change from like the charge to
Because what is the charge? I said proton. Remember, I used the word proton. And if you look, and if you remember from last chapter, the charge on a proton is 1.6 times 10 to the negative 19 coulombs. That's what little e is physically. Remember, little e is on your formula sheet. Little e equals 1.6 times 10 to the negative 19 coulombs. Okay? So because it was a proton, I substituted Q0 with the charge of a proton. If it were an electron, it would still be the same thing with a negative, but I wouldn't even include the negative. Remember, if it's an electron, then I just say, instead of this object moving in the direction it would move, it's going to move the other way instead. Okay? Good question. I want to get into chapter 21 a little bit more. It is more recent. We've done more of it, but I want to go over it still. Any questions on chapter 20, section, God bless you, section 1? Yeah?
Sorry, can you just restate about which direction it goes in?
It depends on which force is stronger, but in this case, because it's closer to the second source, it would absolutely be stronger from this one. But what kind of a force is this one giving off? Repulsion, right? So this overall field would be to the left. Okay? It's closer to the one on the right, but the one on the right is repelling it. Therefore, the overall field would definitely be to the left. E2 will be larger than E1, and therefore our overall field will end up as a negative, meaning it's just going to move to the left. Okay, to the left. All right, let's go into... Now, chapter 21, the first two sections we can do together. But then 21.3 had to do with power. Still involving the same topics, but just a little bit different formula-wise. So 21, we'll look at sections 1 and 2 first. In sections 1 and 2, we recognize first we had Ohm's law. This was our governing formula for all of circuits. For all of circuits, Ohm's law. Now, prior to Ohm's law, we defined what current was. And this is one that, it's on your formula sheet, but if this appeared on your test, it would only be like a multiple choice. It would not be a long answer or something like that. I mean, unless I made it part A and said, this many coulombs past a certain location in 5 seconds, find the current. Maybe you find that in part A, and then using the current in part A and a resistor, you find the voltage and anything else. Okay, but this will be a very simple part of the problem if it were in the math part, where it's like part A, versus it being maybe also in the multiple choice portion. Okay, so current was defined as the amount of charge passing a given spot in a given time period. Well, this is the amount of charge, delta Q. This is the time period, T. And this is what current is. And current is really coulombs per second. Those are my units. And a coulomb per second are called amps. That's what current was defined as to start. Then we went into Ohm's law. Gigi, you got a hand up.
Oh, no, it was like units.
Okay. Then we went into Ohm's law after that. And we used this value here as the current in Ohm's law. That's the current in Ohm's law. Now, V stood for voltage measured in volts. That's one that you pretty much can't screw up, right? Resistance is measured in ohms. And that's that weird looking symbol, if you remember. So get used to writing that symbol. And then current, as we said a moment ago, is measured in amps. Is measured in amps. Are they at the door? No. But a couple of you looked over at the same time, that's why. So V equals IR is our governing equation that we'll utilize. But then we went into a lot more than just that. We went into series and parallel. In series, we had voltage, we had current, and we had resistance. And then parallel, we had voltage, we had current, and we had resistance. And remember, resistance I should actually write in parallel as this, if you recall. Why am I writing 1 over RP for resistance? Everything else I wrote the actual variable. Good. It's the reciprocal sum. Well done. Good statement. So voltage in series, we want to remember, is a sum law. So the voltage that each bulb gets spread out from the source, from the battery. So in your lab yesterday, you guys noticed this. Your voltage, your batteries, what were they around? I know they should have been 1.5. What were they mainly around? 1.4, 1.1, 1.3. They were all a little lower, right? Now, what we noticed was the voltage across the bulb was a little bit less than that also. So if the battery provided 1.4 volts, your bulbs were getting like 1.2 maybe. First of all, why was that happening? Good. The wire and the battery have natural internal resistance. So the terminal voltage on a battery is different than the voltage felt by the actual bulb. Now, you notice that when you added a second light bulb yesterday and you measured the voltage across each bulb, you would have, I hope you picked up on the fact that one bulb got like 0.7 volts, another got like 0.6, 0.7 and 0.6 add up to around 1.3, which was the voltage that your battery provided. So in series, the voltage gets split by each bulb taking some of that energy, sucking away some of that energy. But we noticed that the current, unfortunately, we noticed the current yesterday in series was the same throughout. The current across the first bulb was the same as the current across the second, etc. So again, the difference between sum versus equality laws. But then resistance in series, if you recall, was a sum law. And probably the most important is this one right here. Because God bless you, for all circuits, we need to take all the resistors and simplify them down into one lumped resistor, one equivalent resistance. That's why this one was really probably the most important. Now, what's the difference between voltage and current in parallel versus series? Give me a quick answer. I don't want a whole thing. A quick answer. What's the one thing you do, Daniel?
The current is the same and the voltage goes in different direction.
Okay, good. But give me more. Like, that's much easier to say than all that. It's a very quick, easy answer to say.
It's like sum law, right?
So what happens to the laws between series and parallel? They switch. That's it. That's all it is. They switch. So what was a sum law for voltage becomes an equality law for voltage. What was a equality law for current becomes a sum law for current. Okay, so they switch. And think about why. The easiest thing to remember is the current. The current is so intuitive. If there's a branch, what happens to some electricity? Some goes one way, and some goes the other way. That's why when you branch, current goes to one branch, and some current goes to the second branch. But if I added those currents back together, you would get the amount of current provided by the battery. Current provided by the battery equals the current in branch 1 plus the current in branch 2 plus the current in branch 3, etc., etc. But in series, it's not the case because there are no branches in series. The current given by the battery goes through all resistors equally. Now, the reciprocal law is simply that. It's a sum of reciprocals. Now, I've written all these formulas down here, but you don't have to memorize any of them. They're all on your formula sheet, all of them. Okay, but you need to know how to use them. You need to know why to use them. You need to know why to use them. I might ask you a question like, explain the reason that current in parallel is a sum law. Or explain the reason why current in series is an equality law. Something like that, we have to explain it. So you have to understand how to use this and also how to use it mathematically. Okay? Mathematically. Main laws for 21.1 and 21.2. Now, we're going to do an example together so I want you to see what's happening. I'm going to give you an absolute recommendation. The notes from 21.2, if you recall, we did 3 examples. We did one in all series with 4 resistors. We did one in parallel with the same 4 resistors. And then we did one that was a combination. You recall all 3 of these. You will guarantee you have all 3 of those in your text. Not the same problems, obviously, right? But the same arrangement, the same setup. I want to see your work in series. I want to see your work in parallel. Maybe I'll give you 4 in parallel and only 2 in series. I'm going to vary it, obviously, from the questions in your notes. But then I'm also going to give you one problem that combines series and parallel together. I'm going to go over together with you one that combines them both today. But you need to practice. We don't have time to do them all. Tonight, you definitely practice the simple series by itself, the simple parallel by itself. Because for those problems, we did a little bit more. We found the voltage across each bulb for those. We then found for series. For parallel, we found the current in each branch. So there was more to those problems where it was just series or just parallel. When it's combined, I'm just going to have you find the equivalent resistance and then get the current out of the battery.
Would you give us one like this?
Yeah, and that's what we're going to go over now, something like that. Absolutely, Alex.
Also, will you be able to cover cost today? That was important.
I can, yeah, get to it. Yeah, I hope so. Let me quickly do an example. So I'm going to reduce this circuit real quick. So we've got a battery. I'm going to try to make it pretty simple. All right, so let's take a look at what's going on here. I'm going to give readings for these values. Actually, instead of 7, let's use 6, and it'll make the math easier to do real quick if we're doing this quick. So the voltage supplied is a 12-volt battery. Now, if I were to follow the current, I'm going to use a little cursor here, follow the marker. It's going to leave the positive terminal always. When it gets here, what happens? It splits. So this branch must be in parallel with this whole branch. Everybody agree with me so far? If I look at this branch alone, what are these 2 resistors? Are these 2 parallel or series right here? Series. Because they don't branch in between. We all see that, right? So I can automatically start by reducing my diagram to this. Does everybody agree with me so far? Because it's series, I can simply sum them together. 3 plus 2 gives me 5. I can do that because it's in series. Now, here's the question though. Yes, that there is a branching here, but there's another branching here. So how are these 2 arranged? Parallel with each other, And then this result is in parallel with this guy. Because there's another branch before these two. So this branch causes these two to be parallel. This branch causes these two to be parallel. So we need to take these upper two here and say 1 over RP equals 1 over 4 plus 1 over 6. This is 1 over RP equals, what is that going to be? 3 over 12 plus 2 over 12. I'm going to make 12 my common denominator, so 5 over 12. So RP is going to be 12 over 5. So when I draw this last resistor in here, or not last, but this resistor, its value is 12/5. As a decimal, that's going to be 2.4. Let me just jot down the decimal because it just gets annoying to write fractions. Notice what happens here, people. Notice what happens. The result of a parallel arrangement, what happens to the resistance? 4, 6, 2.4. So what happens?
Goes down.
It decreases. What happens in series? 3, 2 becomes 5. So when resistors are in series, the replaced resistance is bigger than what you started with. Bigger than either of them. But in parallel, the resistor that you replace with is going to be smaller than even the smallest of these 2, 3, 4, however many there are, always. So when I combine these next two, 5 and 2.4, and they're in parallel, you can already guarantee me what? Loose? It's going to be lower than either 5 or 2.4 for sure. So let's go ahead and look at that. 1 over RP, so now we're on the second one. 1 over RP equals 1 over 5 plus 1 over 2.4. I cannot do this in my head. I'm not going to do this in my head. Tell me what we get, please, real quick. Somebody that's quick with their math. Obviously on a calculator, I want you to do this. 1/5 plus 1 over 2.4, enter, gives me 1 over RP, and then invert it afterward. Give me both though, please. So what's 1/5 plus 1 2.4? Is that right? You said it? What do you got? 1/5 plus 1 2.4, Sid.
37 over 60 and then inverted 60 over 37.
37 over 60. He used the convert to fraction button on the calculator. And then what was the other one? If you give me a decimal for it, please.
A decimal
For 60 over 37, just type it in directly. 60 over 37, enter.
1.62.
Thank you, sir. So, we look at the overall circuit. We see this, that's a 2 right there, that's a 2. We see that the final result is 1.62. As Lucy said, it's lower than both 2.4 and 5 ohms. That is correct, it's logical, it's sensible. If I have the overall voltage and I have the overall resistance, what can I find? The current. Very good. Okay, I'm not going to go through the math. You guys can solve on your own. Just divide both sides by 1.62. Okay, that'll give you the current there. That's how you're going to simplify a more complex circuit. Okay, I'm not going to go into problems like, now find the current across each resistor. Find voltage on one of those resistors. I'm not going to get into all of that stuff. Okay, that is a little bit more advanced. Not that we can't do it, but because of time, we didn't really get a chance to do that kind of stuff. Okay, so I'm not going to test you on that. So this is the extent to which you'll be tested for a multiple resistor parallel series circuit.
In some of the homework problems, it would say that find the potential difference. And then
Voltage. Voltage. They're synonyms, absolutely. Because remember, one end of the battery has a certain amount of potential. The other has another amount. It's a potential difference that they have. So remember how this works, right? I have a charge carrier. I leave the battery with a lot of energy. I get to the battery takes away all my energy. I leave the bulb takes away all my energy. I go back over to the battery. I hit the beginning of the battery with very low potential. I get to the other end of the battery and I've got very high potential difference on a battery voltage. Okay, very good question because that is definitely useful. That diagram with the potential energy of a charged particle, good stuff to know for sure. Okay, good stuff to know for sure. Let's get into 3 so we can see power. So for 21.3, if you recall, we had 3 formulas for power. First, second, third. Which one are you going to use tomorrow on the test? Which one are you going to use tomorrow on the test?
V equals IV.
Why?
Because the each is 1.
What's the real answer? Somebody help me out.
So the V has the I and the...
What's the real answer? Somebody help them both out. Come on.
All of them.
Maybe all of them, maybe one of them. It depends on the scenario. If you give, listen, right? If you're given resistance and voltage, go to the third one. Sure, you can find current using V equals IR and then use the first one, but why do an extra step? No need to do an extra step in these problems. So those are the 3 formulas for power. Now, cost was equal to the amount of energy used in kilowatt hours times the rate in dollars per kilowatt hour. I'm putting units in brackets as always. This is how we measure cost. So if you recall, power is really energy over time. This is from like earlier in the year. The definition of power is the rate at which energy is lost or gained. So power is energy over time. How would I solve that red formula for energy? What does it become? Energy equals? Good. P times T. So really, look at the formula, people. Kilowatt times hour. Kilowatt comes from power. Hour comes from time. So when you want to calculate the energy used, do power times time. But if you don't remember this, it's on the formula sheet as this, earlier in the year. So just rearrange it to solve for energy, and then use power times time, but that's also the units. The key to remember here is that your power has to be, again, in kilowatts, and your time has to be in hours. Once you calculate the energy that your apartment, house, whatever uses, you could then multiply it by the rate I give you in the problem to find the total cost, and that cost will be in dollars. I don't know, it's dollars, kilowatt hours times dollars per kilowatt hour. Gigi.
I was having a hard time figuring out what energy was, so it's just power.
Power times time. Power time, right here. Energy is power. Look on your formula sheet if you want it right now. Find this formula and just write a note that you can solve this for E to get P times T, and that's power, kilowatt, times hours.
So you need to change watts. Because when you solve that, you're going to get watts, right?
Absolutely. When you solve this equation to do this, or when you're given power in a lot of problems, I'll give you power in watts. Or you might have to find the power in part A using these. And you'll have the power in watts, convert that to kilowatts.
Okay.
Move the decimal 3 spots to the left to go to kilowatts.
I was going to ask
Okay.
that.
Okay? So we all see how this is going to be a 2-part problem, right? I mean, look, that's part A, that's part B. You can already predict what's going to be on the test. I'm going to ask you to calculate power at some point, that'll be part A. And then part B is the cost. Maybe part A is use Ohm's law to find V or I or R or something else. Then part B is find the power. Then part C is find the cost. Maybe part A is find the current using delta Q over T. And then once you have the current, I'll give you maybe the voltage also. Then you find the power. And then you find the cost after that. So there could be many ways I could ask this to you, but know that I will step you in that direction. Part A affects part B, which affects part C. That's how all AP exams and SAT subject test type tests are kind of made, so that the first part affects the next. Okay, if you can't get the first part, what do? What did I tell you to do if you can't get the first part ever in a multi-step problem?
Pick a number that makes sense.
Pick a number that makes sense or is reasonable. So if it's watts, maybe 20 watts, not 600,000 watts, because the numbers we're looking at for watts are not that large. But pick a given number, or pick a random number really, and use that number for the successive parts. Okay? This is kind of it for the review. What other questions do you have still? Were there any particular problems you struggled with that you want to ask about while we have, I don't even know how much time at this point.
Talk about a pentameter again.
Sure. And I spelled that wrong. I spelled that word wrong in your notes. Potentiometer. That's the right spelling. I spelled it as pentiometer. I forgot the OT. Look, it's potentiometer. I spelled it as pentiometer. I don't know how that was a mistake. Anyway, a potentiometer simply varies the resistance. It's a variable resistor, a joystick, a light dimmer. As you change the resistance, you're changing the amount of power. Take a look. If I were to think about this, power is V squared over R, right? So watch what happens. If I change the resistance in an item, in an element, in a circuit, I'm not changing the voltage, I'm just changing the resistance. The voltage is supplied by the battery. So if I change the resistance, right, and let's say the resistance goes up, the power consumption is going to go down. Okay? So you get a brighter or a less bright bulb based on adding or removing resistance by turning that knob or by pushing on that joystick. Okay, that's a potentiometer. Good question. Great question, because that's like multiple choice, right? Or short answer, those types of questions. Short circuit, open circuit, circuit breaker. Phrases that we should know. Anybody want to ask anything about any of those? Circuit breaker, short circuit, open circuit, closed circuit, those phrases. All of them. Short. All right, open. All right, let's start. Closed circuit. Boom, there you go. It's closed. There's no gaps in the circuit physically. An open circuit would be if I took a scissor and sliced it right there. And then the circuit would look like this.
No, like the light wouldn't turn
That was
on.
like one on the last, right?
Correct. So in the first case, the energy from the battery would go to the bulb. The bulb would light up. But then if you take the alligator clip off, that's like doing this. And then it's an open circuit. When you took the alligator clip off, did it light up?
Because then the electrons like aren't going.
The electrons can't jump this gap. It's like creating a gap in a river. You can't just jump over it. You need a bridge to bridge that gap. When I turn the light switch off, I'm opening the circuit. Remember that? We talked about it. That's misnamed. When I turn the light switch on, I'm closing the circuit. A switch is exactly that. A switch in a diagram looks exactly like a lever. Take a diagram like this, and that's an open switch. Take a diagram like this, and that's a closed switch. Okay, so a closed circuit,
Closed works, open doesn't.
open circuit. This is an open switch, and this is a closed. Hey, by the way, what's another word for a closed switch? A circuit breaker is a closed switch. Even in diagrams it's drawn like this. If the circuit breaker senses too much current and the wires might start to burn, short circuit, this will flip open and the breaker will literally pop. And that's when you have to turn it back in place.
So is that in like all the devices that we have?
Yeah, what? Only in like your house. That's in the wall, the panel in the wall. A power surge is a circuit breaker. So you can have this that's still a short circuit, but the energy would naturally, there's this because if one branch has no resistance at all, it'll all go that way. It's only when you